Second part of our lecture will be on energy. For energy, we need to know the different types and how to convert one energy from one type to another. The first energy that we all know of would be kinetic energy as given by Ke, and potential energy given by Pe. There are a few types of potential energy. One that we commonly use would be gravitational potential energy. One that we learn in forces would be elastic potential energy. There's one more potential energy that you may not know of, or may not know of it as clearly. Right, this is the electrical potential energy. Now, we know that energies are neither created nor destroyed, so energy is always conserved. We also know that because energy do not always stay in the same form, if you were to throw, for example, a ball upwards with a certain kinetic energy, the energy will convert from kinetic energy initially to potential energy at the height, at the maximum height of its flight. Because it has slowed down, its velocity goes to zero. All of the energy goes into the potential energy as it gains a maximum height. When the ball falls back down again, the potential energy is changed back into kinetic energy as it reaches back to the maximum velocity at the point before it hits the ground. Now, there is a need to know how to derive and apply the kinetic energy. Here, we will only teach you how to derive the kinetic energy. When we meet on Monday, we will learn how to apply some of these equations on some of the questions. So first up, if you apply a certain force F to move an object M across a certain distance, and we assume that there's no friction on the ground, the work done by this force, which is a certain energy of unit joules, will become the kinetic energy of the object as the object moves faster and faster. Now we know that kinetic energy is given by work done, and work done is given by force times distance. And we know also that force is given by mass times area. We can easily say that kinetic energy of the object is given by mass times acceleration times displacement. Now if we use what we know from kinematics, we know that v squared equals to u squared plus 2ad, and we know that the initial velocity of the object is 0. We can easily know that v squared is equals to 2ad as u equals to 0. Now if we now then take a as the subject, we know that v squared over 2d is equals to a. Now if we substitute this back into the equation, we get simply ek equals to m bracket v squared over 2d times d. Here it's very convenient for us to cancel out the d's because 1 is a denominator and 1 is a numerator. And what do we get? We get ek, which is kinetic energy, equals to half mv squared. And this is the commonly used and well-known equation for kinetic energy.